Okay folks, so in our previous video we saw that we could solve a particularly messy trig equation if we knew some helpful identity to push us forward. And that was one of our double angle identities. There's several double angle identities, and there's also several ways to write each of those double angle identities. And we derived in the last video that the sine of 2x was equal to 2 sine of x cosine of x. And I've asked you to memorize that. I have two more double angle identities for us to memorize, and we're going to derive each one of these, but I'm going to present these identities as the way you're going to use them most often in Calculus 2. And I don't mean to say this is the best way to memorize it, but for those of you going on to Calculus 2, this is how you will typically use these identities. Sometimes they will be called power reduction identities. So the first one is that if you have the sine squared of theta, you can write that as 1 minus the cosine of 2 theta, all divided by 2. And if you have the cosine squared of theta, you can write that as 1 plus the cosine of 2 theta, all divided by 2. And so sometimes these are called the power reduction identities. And I'm asking you to memorize these. So I would recommend putting this on one side and put the double angle identity for sine squared on note card, and put the double angle identity for cosine squared on note card, and then write this on the back. So it is important that you have those memorized, especially for Calculus 2. And what I'd like to do is I'd like to derive one of these, and then I'm going to give you the challenge of deriving the second. I'll give you one key hint for that. So let's go ahead and start by deriving this double angle identity, or this power reduction identity. So I'm going to go ahead and start with the cosine of 2 theta. And if you're saying, Charles, I don't see why it's clear that I should start there with this work, I agree. And I don't think I would expect a student to be able to do this without me showing them how to do it their first time. Okay. Nonetheless, we're going to start with that kind of inner term here, and we're going to do some manipulation of it. And this is similar to the manipulation that we did before, where I'm going to write this in a clever way. I'm going to write it as cosine of theta plus theta. And then we'll make use of our sum difference angle identities for cosine. So as a reminder, if I take the cosine of alpha plus minus beta, that this was equal to cosine alpha cosine beta, and then watch it, minus plus sine alpha sine beta. So this was the sum and difference angle identities for cosine that we tested you on in the last unit. So here again we're going to use alpha is equal to theta and beta is equal to theta, and that's a little bit strange, but it does propel us forward with this problem. So I'm going to go ahead and write this as the cosine of theta cosine of theta, and then careful here, we're using the plus symbol, so this would be minus the sine of theta, applying that double angle identity. Doing a little bit of simplification, we can write this as the cosine squared of theta minus the sine squared of theta. Okay. Now here we have a choice. We could replace cosine squared with something, or we could replace sine squared with something. So we could replace cosine squared of theta with 1 minus sine squared of theta. Or we could replace the sine squared of theta with 1 minus the cosine squared of theta. Both of these are making use of the identity that cosine squared theta plus sine squared theta is equal to 1. So I'm going to take and replace one of these expressions with a variation of the other using my Pythagorean identity from the last unit. So notice that this identity here relies on knowing both your sum difference angle identity and your Pythagorean identity. So this is why this is so tough, and this is why I want to derive it with you. Well, if we look at what we're eventually trying to derive here, we'll notice that we want to have only cosine squared theta show up. So I'm going to do 2 in this problem here. So we'll do 2. When I ask you down below, I'm going to ask you to do the same thing, but you're going to derive the double angle identity for sine squared. This is where you're going to change tack. When you get down to this point in your problem, you'll do this in number 8. Okay, so let's backtrack because I feel like this is a lot of information at once. Let's try this again. We started off with the cosine of 2 theta. It wasn't clear to me that that's where I should start this problem, but that's what I started with. And we wrote it in a clever way as the cosine of theta plus theta. Why was that helpful? Because it allowed us to use this double angle identity for cosine from the last unit. And then we went ahead and applied it here. So we rewrote this as cosine theta minus sine theta, and then we went ahead and multiplied them out. And you'll see here that we sort of have most of the elements that we're looking for in the expression that we're wanting to derive, except that we do not want a sine squared theta to show up in our final derivation. So I'm going to replace sine squared of theta with 1 minus cosine squared theta. So let's try that here. This is equal to cosine squared theta minus, and then I'm going to replace all of this with 1 minus cosine squared theta. We're getting a little bit closer to our eventual answer. So this gives me cosine squared theta minus 1 plus cosine squared theta, or 2 cosine squared theta minus 1. And I'm going to go ahead and just put that in a different color because that's actually where I wanted to stop. Okay. So we've now just shown, that the cosine of 2 theta is equal to 2 cosine squared theta minus 1. So let's go ahead and solve this now for cosine squared theta so it looks like the way we want the identity. By the way, sometimes books will give the identity this way, which is perfectly fine, but when I go to use the identity in Calc 2, more often than not, I want to solve for cosine squared. So I'm going to go solve this for cosine squared. So when I do that, if I add the 1 over, we would have the cosine of 2 theta. We're going to add that 1 over. I'm going to lead with that 1 when I add that 1 over, is equal to 2 cosine squared theta, and then I'll divide this 2 over, and so we get 1 plus cosine 2 theta, all divided by 2, is equal to cosine squared theta, and that is exactly what we wanted to derive. Whew, that was tough, folks. Let's recap that briefly. We started with this cosine 2 theta. We wrote it in a clever way, applied our double angle identity, and we were left with an expression involving both cosine squared and sine squared. Oh, it's important to note that this expression right here, that expression right there, does not equal 1. It would if this were a plus sign, but it's not. Then what we did is we said, well, we're trying to derive the version of this that has only cosine squareds in it. So I took my Pythagorean identity and I replaced sine squared with 1 minus cosine squared. That's what I did here, and then we just sort of cleaned up the work to get to this result. Once we got to this result, while this is a perfectly good place to leave your double angle identity, when you go to use it in Calc 2, you'll want to have it solved for cosine squared. So that's what I did. Okay. So folks, I would now like to leave you with this last problem where you're going to use this example above, and I want you to try to derive this identity here. My hint is what I wrote up above here. When you get to this point, you're going to start in the same place. You're going to, so in fact, let me roadmap it for you. You're going to start with cosine 2x. We're going to start with the cosine of 2x. We're going to write it as cosine of x plus x, just like before, and you're going to get down to an expression like this, the same expression, only involving x, and you will replace the cosine squared x with 1 minus sine squared x. That'll get you pretty close. And then once you get even further down, you will solve for sine squared x. That's all the hint I'm going to give you. I'm not going to give you the answers problem. I would like you to please spend 15 minutes trying this. If you get it, great. If you don't, that's fine. You will have spent 15 minutes struggling with it. And so then when we go to, when we deal with it again in class, you'll be more ready to see the proof. And so I'll have you do this in your groups in classes to finish out proving this identity if you don't. But please spend 15 minutes reviewing the work that I did up here in number 7 and then trying to modify the work for number 8. Give it your best shot, folks, and I'll see you next time. Bye-bye.